Okay, now substitution is a super useful tool. Kind of feel like it should have been taught a little bit earlier, but I mean, we're still really new to the integration thing. But it gives us a way to evaluate integrals that may be otherwise complicated. The big thing is you're trying to decide what is your u going to be such that its derivative is showing up next to the function. And you'll see as we get into that. So you have to use a little bit of sometimes intuition. Sometimes you have to manipulate things, divide, multiply to make it line up with what you want it to be. Okay, so it essentially is using the chain rule. So if you have an outside function and an inside function, the derivative, if you recall, of a composite function is the derivative of the function times the composite function. So we're going backwards with this. So if you would consider that f was a derivative already and g is the inside function, its derivative would show up as times something else. So it looks bad to begin with, but it usually cleans up very quickly. So let u equal g of x, the common variable for substitutions. There's u and there's v and there's w. U is most common, then v. And when you get into, if you take calculus 2 next semester, you'll get into integration by parts, and we'll use u and v. So let u equal g of x, where g prime of x is continuous over the interval. Let f of x be continuous over the corresponding range of g, and then let f of x be an antiderivative of f. Then, drum roll, what happens? The integral of f of g of x times g prime of x can be reduced simply down to an f of u du, and then you can integrate that and you can plug back in your g of x. So this is it for indefinite integrals. So that means you don't have the limits of integration. And there's another little subsection that we'll do with definite integrals. And they're very similar. They're just one more step in the process there. But the idea is you can substitute, put the u in there, and then when you're all done, it's clean and straight to go plug in this what u was. It always sounds like I'm using bad grammar when I do that. So what was u? So let's do one. So here we have this integral 6x times the quantity 3x squared plus 4 to the 4th power. It's always pretty sure bet that this stuff inside, that's your g of x, or that's our u. We're going to say u equals 3x squared plus 4. And if that's the case, what would that derivative? If they took the derivative, then they're going to end up with that chain rule applying. So there's the derivative of what was inside. So what's the derivative of the stuff inside? What's the derivative of 3x squared plus 4? We call that du. What is du going to be? 6x dx. And we finish off with a dx. So notice that over here we have the 6x and we have the dx. This part right here, that's our du. And we can rewrite the entire integral as the integral of u to the 4th power du. Because u is this stuff in here, that's our u, is a 3x squared plus 4. It's being raised to the 4th power. The du is that derivative of that stuff inside, 6x dx. And now if we integrate, how would you integrate a u to the 4th power? How would you integrate something to the 4th power? Nothing's, no tricks here. What do we do when we have something to a power? Well, we would add 1 to the power and divide by the power, right? Okay, so we would call this u to the 5th over 5 plus c. That's the big step there. We add 1, divide by that power. And then I asked the big question where my grammar sounds bad. What was u? Yeah, so it's 3x squared plus 4 to the 5th power divided by 5 plus c. And that's it. Doing the u substitution. Now, an alternate form of this, I'm not going to do this. You could expand the 3x squared plus 4, right? You can expand that binomial expansion big time. You multiply everything by the 6x and do every single term, and then come back and factor if you want. I wouldn't. I mean, we have these tools for a reason. So let me just recap on this. The stuff inside the parentheses, that's my inside function, that g of x. that we saw back in our derivative days. We had inside and outside function for chain rule. That's that inside function. We're going to call that the u. Then we're going to take and get its derivative. And hey, look, the derivative is there. Derivative and the dx is there. So that's my du. And I can rewrite how it looks, make it look easier and cleaner, integrate, and then substitute back. That's the substitution method.
So what happened with the du?
Well, in integration, it goes away just like your dx does. It's just note that we're at a point where these variables need to match. You will reach a point where you might have a dx and it might be an x squared y inside, but don't worry about that. That's calculus of multiple variables, and you'll get that in Calc 3. But for now, these should be matching. I could say more, but I feel like if I do, it's just going to take us down a rabbit hole that's going to confuse people. So, okay, let's try another one of these. What do you think in this case? Integral 3x squared times the quantity x cubed minus 3 quantity squared dx. What would the u be in this case? What's the inside function here? Yep, so I'm going to say u equals x cubed minus 3. So if I choose that to be my u, you have choices on what the u is going to be. So we choose that to be our u. What is the du? What's the derivative of that? 3x squared, and we tack on the dx. I'm going to be honest, when I was a student at this point, I'm like, why are we throwing the dx in there? Because that's part of that derivative, the integration stuff. So we're just trying to keep track of it all. This 3x squared dx, that's my du. This is my u right up there. So this becomes just a u squared du. I mean, let me show it this way. I could rewrite that integral as x cubed minus 3 squared times 3x squared dx, such that this is the du now, and then this is my u squared.
How come we're not taking the derivative of 3x squared and then tacking that on into?
Because that is the derivative. That's that leftover part of the chain rule. So if you remember our chain rule, if we had, well, let's take this last one, for example. If we took the derivative with respect to x of 3x squared plus 1 plus 4 to the 5th power over 5 plus c is just some constant, so that's going to go away. What's that derivative going to look like? Well, I'm going to have 5 times the 3x squared plus 4 to the 4th power over the 5. Those will cancel. But then I have to multiply it by the derivative of what's inside. So the derivative with respect to x of the 3x squared plus 4. And that's where we get the 3x squared plus 4 to the 4th power times that derivative is 6x. So it's undoing the chain rule. So back to here, what is our antiderivative of u squared? U cubed over 3 plus c, very good. And that u was 3x, no, just x cubed minus 3. That's it. Not so bad. We're going to crank up the difficulty a little bit, just a little, just slightly. So these last two problems we did, when we took the derivative of the inside, we had that outside function sitting there exactly. It's like it's already prepared for us to use. Now we're going to do a little bit of manipulation. Sometimes it's going to happen. You have to do some manipulation to make it appear the way it's supposed to. And it's not that bad to do. So what do I mean by that? Here's this case with the z's. We have the integral of z times the square root of z squared minus 5 dz. Now, what would you choose as u in this case? If there's something going on, something being raised to a power, like a quantity raised to a power, or a square root, or something e to a power, that special thing is what we're talking about. It's going to be your inside function. So in that case, the u here is the stuff under the radical, which is z squared minus 5. So now we think of what is the derivative of z squared minus 5? 2z, very good. So du would be 2z dz. Now, if you look what we have here, I'm going to rewrite this to make it a little more user-friendly. Integral of the square root of z squared minus 5 times z dz. I have a z dz, not a 2z dz. So it's not exactly like it should be. Are we out of luck? No. Because we have constants like that that aren't where we need them to be, we can make things as we need to. We can divide both sides by 2, and we could say 1/2 du equals z dz. So this can be replaced with a 1/2 du instead. And now we can write this as 1/2, I'm going to put it out front, integral of the square root of u du. So again, that 1/2 is there. There's the du. That was the z dz. And something like I say in CDC. And then I have the square root of u. And for my sake, I like to write these as integral of u to the 1/2 du. So u to the 1/2. I personally do that. That's my way of doing things. Doesn't have to be your way of doing things, but I can see antiderivative is easier when it has a power. So I'm going to add 1 to that power. What's 1/2 plus 1? 3/2, and then divide by the new power. So this 1/2 here is from out front times u to the 3/2 divided by 3/2 plus some c. So I add a 1 to the power divided by that new power. Here's where it gets a little interesting. I mean, we have to deal with this would happen in any case, anytime you have something to a fractional power. So 1/2 times, so 3/2 being in the denominator means you could flip it and make it 2/3. Then we have our u was really just a z squared minus 5 to the 3/2 plus c. And those 2's divide out. So it's going to be z squared minus 5 over 3. Z squared minus 5 to the 3/2 over 3 plus c. And that's it. Let's do a few more of these. If we can get the pattern down. Someone's having fun out there. They're probably doing calculus homework. See how much fun this will be. Okay, ready? Okay, here's another one. So again, it's not going to be right across the board. So we would come up with u equals what in this case? X cubed plus 5. So du is (3x squared dx). Very good. And we don't have a 3x squared dx. We have integral of, and we write this x cubed plus 5 to the 9th times x squared dx. We have the x squared dx. So what do we need to do with that?
Multiply by 3.
I could divide by 3. So 1/3 du equals x squared dx. So now this can take the place of that part. And this takes the appearance of integral of u to the 9th times, I'll put the 1/3 out front, du. So what is our antiderivative of u to the 9th? One-third u to the 10th over 10. That's times there, so it's u to the 10th over 30. Oh, I forgot my plus c. Yeah, forget all that. Just throw it away. 1/3 u to the 10th over 10 plus c. So I'm going to end up with x cubed plus 5 to the 10th power over 30 plus c. By the way, you could write that as a 1/30th out front instead of under as a fraction there. Okay, now we're going to look at something that you all enjoy so much. I'm hoping you actually do. I say this jokingly, but sines and cosines derivatives, antiderivatives. By the way, we're getting close. After substitution, which is 2 parts, we may not get to the second part today. We will get to the next thing is integrals for exponents and logarithm functions. And that's the day you want to be here. I'm hoping for Wednesday. I mean, you all want to be here every day anyway. Okay, so here we have a situation. It's an integral of sine t over cosine cube t. And this could actually present itself in many forms. Like it could have been something like integral of tangent t secant squared t dt. And you can go back and put it in this format in terms of sines and cosines. So if you remember your math 127 days, a lot of the times you'd boil things down to sines and cosines. So this looked really, really bad. Like, oh my gosh, what am I gonna do? I got a sine on top, a cosine cubed on bottom. Well, one way to consider when you're dealing with sines and cosines, the part that's what I would consider like the active portion is that bottom part, because that's got the power to it. And if you were to say in this case, u equals cosine of t, what's the derivative of that? What's the derivative of cosine? What's that? A positive sign. Sine t dt. So, oh, you're right. It is negative. I apologize. You're right. Derivative of sine's positive cosine. So thank you for good job. Okay, so we have a positive sine t dt. So you could say negative du equals sine t dt. So this becomes instead integral, I'll put that negative out front, of 1 over u cubed du. You can handle that, right? I personally don't like the way that looks. I see things easier this way. Again, it could just be a me thing. Okay. Negative of u to the negative 3 du. Yeah, I'm going to say as your instructor here, I don't want to teach you bad habits. They're both equivalent. If you're good at integrating 1 over u cubed and making that negative 1 over negative 1/3 over u squared, negative 1/2. Anyway, that's why I don't do it that way. I do it this way. So I have negative. That's going to become a u. I'm going to add 1 to the power, u to the negative 2, divide by negative 2, and then add c. And this cleans up a little bit. The negatives cancel. Becomes 1 over 2u squared plus c, which is 1 over 2 times cosine t squared plus c. And that's the answer. So sines and cosines actually can be helpful and clean up nicely because the derivative of the sines, the cosine derivative cosine's negative sign, and then those go away pretty quickly. But when you first see them, they seem like, oh my gosh, there's so much there. Okay. Okay, I do want to try this next one, and I had some on the next page. I would like to get through this whole subsection, but if we don't, I also would want to take some time for questions if we can. Let's do this example. I want to do 7, and then I want to take some questions if we have them. Because I think the rest of them are just repetition of what we've been doing, and it is, okay. Okay, so in this case, again, what would you call U in this case? I would just call it, I'm glad they wrote it like this to do it, but what is happening here, just to at least see it, this is sine t, that amount's being squared. So I would say U is just the sine t. So you're gonna have with the U squared in the denominator. So what would du be in this case? It'd be cosine t dt. So you end up with the integral of 1 over u squared du, because here's our cosine t dt, that's our du. Excuse me. And again, I'd like to treat this as u to the negative 2 du. So what would that be if you integrate it? U to the negative 1 over negative 1 plus c, or 1 over negative u plus c. And what was u? Sine t. Should be corrected. Yeah, okay. So again, this is doing substitution for indefinite integrals. Next time, we're going to get to the definite integrals, and we're going to get to integration for exponentials and hopefully logarithms. So now, this is one I think is worth doing because it's just a little bit different than what everything else we've been doing. So here's another sine cosine 1, and the following one's a sine cosine 1. So I think you can handle that now. So in this case, we have the integral of x over the square root of x minus 1. And when I see something like this, well, I'm thinking, well, if my u was x minus 1, my du is just a dx because the derivative of x is 1. So what's going on here? So this is kind of where they mess you up a little bit, and I apologize if that's what's going to happen. When you're doing something like this, still go with u as that stuff under the radical. But if you notice on top is just an x. So if you know u equals x minus 1, if you add 1 to both sides, you have a way of writing this as u plus 1 equals the x. So the top becomes u plus 1. The bottom becomes the square root of u. And of course, that's a du. So we can rewrite this whole thing as the integral of u plus 1 over the square root of u du. So now if that looks bad, it's not that bad because you have a single term on the denominator, you have 2 terms in the numerator. So you can separate them out by saying integral of u over the square root of u plus 1 over the square root of u. I don't call this a trick. This is really a strategy and how you deal with it when you have this kind of representation that you have the square root of something and then a single term on top that you can turn into 2 terms, and you were able to do this split up the numerator. You can't split up the denominator. You'll learn in Calc 2 a way of doing partial fractions if you haven't already learned that. Fun, and I mean that, I like that process. Not the scope here though. So this would be the square root of u, and I'm going to call this plus u to the negative 1/2 because that's u to the 1/2. Maybe I should do that in steps. 1 over u to the 1/2. So this becomes the integral of u to the 1/2 plus u to the negative 1/2 du. Okay, and you know how to evaluate this now. What is our antiderivative of u to the 1/2?
Three halves over three halves.
Good, and then u to the negative 1/2, what's that one going to be? Over 1/2. Good, plus c. So we have 2/3 times u to the 3/2 plus 2 times u to the 1/2 plus c. That's going to be 2/3 times x minus 1 to the 3/2 plus 2 times x minus 1 to the 1/2 plus c. That's it. Okay, so with that, I'm happy to do more examples, but I want to take time to answer homework questions if you want to see some homework questions worked.